Listen, just want to remind you that our test is coming up. It'll include chapters 3, 4. Might include a little bit of chapter 5, we'll see. I mean, we'll finish up chapter 4 soon, but we'll see how far we get at chapter 5. So it might include part of that. That's a lot of circuits, so make sure in the meantime that you can do combination circuits and that you understand the definitions of current and power. Make sure also that you can do multi-loop circuits. You'll definitely see a multi-loop and a combination circuit, so make sure that you can do that. And then you'll see some household circuits and RC circuits like we're going to do today. And in fact, the RC circuits, we're going to see a lot more capacitors in the next month or so as we wrap up the class, because we're going to look at how resistors, or excuse me, how capacitors work in circuits when we involve other components like inductors, for example. And then we'll also get into AC electricity. So basically we're doing circuits for the rest of the semester. Chapter 5 will be magnetic fields, but that'll be important for our understanding of inductors. We're going to see some different kinds of calculus come in, and then at the end of the semester we'll even do a little bit of differential equations. But I'll show you, it's going to be all very basic stuff. I know that many of you have not had differential equations, or you're not required to take it, but you chemistry majors, you are, right? Differential equations, you take that class? No, well, if you go to graduate school, you'll probably see it. And so we'll just sort of give you a brief little introduction to those. Are you engineering students? Pretty sure you take differential equations. All right, so let's look at RC circuits. Mainly in this part, you know, if you go on to graduate school, you might see circuits as you build instruments, if you build your own instruments. But mainly I want you to come to understand the exponential growth and decay curves. For you biologists, you'll see this a lot because it comes up in life systems a lot. So we'll look at the exponential growth and decay and just learn, you'll need to practice on how to solve those for particular things. Learn how we characterize these growth and decay curves. When I have an exponential growth curve or when I have an exponential decay curve, how we characterize those by the time constant and how we solve for particular values in that, and just what they look like. As I said, this will be important for other circuits that we'll look at later, LRC and LC circuits, because they'll operate in a similar way. So in circuits with capacitors, the current varies with time. When you turn the circuit on, you know, when you close this switch, the capacitor will charge and the current will be waning. That means that initially you'll get a really big current as you're moving charges from your power supply. You move your charges from your power supply to the capacitor, and then charges also are moving in this direction to here. So if we think about it in terms of positive charges, we get positive charges that move onto this plate of the capacitor, and then negative charges will move from this plate onto the battery. Although we know that really the opposite is happening, that negative charges are moving from the low potential side of the battery to this plate, and then that's forcing negative charges away in this direction. Remember, there's never actually any current flow across the capacitor, but there definitely is current flow through the circuit as you move charges onto this capacitor. You're charging up the capacitor, developing this distribution of charge on the capacitor as you get more and more charge on it. Remember, there is a maximum value for the capacitor, the charge on the capacitor. We saw that in chapter 4. It's equal to C times V. That's sort of like the Ohm's law for capacitors, y'all remember? Q is CV. Right? That is the maximum value. So this is our maximum value on our capacitor. And initially, I'm going to get a big current. Do we need to stop, Dustin? Oh, that was you, Nicole. Okay. All right, thank you, Dustin. Initially, we get a big current, and then it decreases with time. As you add charge to the capacitor. It wanes, it gets smaller. We describe this, there's a function that describes how this occurs. It's an exponential function. And our Q is going to equal to our maximum Q times 1 minus e to the minus t over RC. Now, you've probably seen the exponential function before. You should have. If you haven't, that's okay. The way you do this in your calculator is the not the EE button, but it's second usually to which button? Do y'all know? The natural log, right. In fact, we'll use the natural log to solve for values that are in the exponent of this exponential. E actually has a value. It's like, what, 2 point something. It's a number, all right? So make sure you know how to do that in your calculator. There's some practice problems in the homework. Just make sure that you can get the right answers with your calculator and go through the mechanics of that. We'll do some practice problems in class too. But if you have trouble doing that with your calculator, I know a few of you will, at least a few of you will have trouble, please come see me, I'll show you. Remember, it's not the EE button, it's the E button, which is second to the natural log. This Q value is equal to C times V. That's our maximum charge. And in a similar way, we can calculate the current. So our current is equal to our maximum current times e to the minus t over RC. This function is a growth function, and this function is a decay function. All right, the charge is going to increase on the capacitor. As time goes by, the charge will increase. As time goes by, the current will decrease. Because remember, the current starts out big initially, and then it decreases. I can rewrite this function as my I max is going to be V over R times e to the minus t over RC. Right, because V is equal to IR, so I is equal to V over R. Initially, you get maximum current as you would have it, say, in just a regular circuit just with a resistor. Go with me so far? Yeah? All right. Make sure you can recognize these curves and where they apply. So make sure you know that this is what happens to the current for a charging capacitor, and this is what happens to the charge for a charging capacitor. By the way, this would also be, or which of these would give us the voltage across the capacitor? Which of these would give us the voltage across the capacitor? Which of these curves would define the voltage across the capacitor? What's going to happen to the voltage across the capacitor? Is it going to increase or decrease with time? Well, let's think. The voltage across the capacitor, what is that equal to? Well, what is it dependent upon? The voltage across the capacitor. The what? The charge, right. So the more charge I get on the capacitor, the more voltage I'm going to get. When I'm fully charged, that means that whatever voltage I had on the battery, I also have on the capacitor. So which of these then would define or would describe the voltage of the capacitor? Would it be this one, the one on the left, or the one on the right? The one on the right, right. So we can also write here that this is the, how do we say this, the voltage across the capacitor as well. That function would describe the voltage across the capacitor. All right, can I go down from here? All right, so after you charge the capacitor, the battery can be removed, and then we get a circuit that looks like this. I have a charged capacitor, and it acts sort of like a source of potential, kind of like in that car, that crazy guy that's probably up in Vermont, or he's not crazy, but probably like up in New England or somewhere, where he has the capacitor that he used to drive his car, or to start his car. I have a fully charged capacitor. It will discharge through the resistor, and it acts as a source of potential. And all of these, the charge, the current, and the voltage, they're all going to decrease with that exponential function. So they're all going to look like this. They're all going to be Q, big Q, that's the maximum charge in the beginning, times e to the minus t over RC. So remember, that graph is going to look like this, Q over time. It's going to decrease with time. It's going to begin right here at big Q. In a similar way, I is going to be V over R times e to the minus t over RC. And then V is going to be V initial, whatever my initial voltage was, which, by the way, is going to be, what is it, Q over C. Isn't that right? Q is C, V, yeah, times e to the minus t over RC. And so this is also equal to this, Q over C, e to the minus t over RC. right, so we get those three different expressions for a discharging capacitor. Look, these are all on your equation sheet, so don't bother memorizing them, but you need to recognize when you look at this function, you say, okay, this, because it's missing a 1, is going to be an exponential decay function. If you think about this, this is e to the negative exponent, and so as that exponent gets bigger, then this value approaches 0. And that's what you see here, that the value approaches 0. Whereas if I have 1 minus that number, as that value approaches 0, the function approaches 1 times whatever the maximum value is. You follow what I'm saying? This is a fraction, right? This is in the denominator, this whole thing, because it's a negative exponent. So it's 1 over some number. And as this number gets big, then that quotient approaches 0, because 1 over a big number is 0. 1 over infinity is 0. Y'all clear with me how this works? Just mathematically? Right, you'll see as we get close, we'll sort of do a few. Okay, so we talk about a time constant as a characteristic time, and we use that to describe how long it takes to charge or discharge. But let me be clear that the time for charging or discharging a capacitor is not given by the time constant. Yeah, in a time constant, you get something like 67% of the full charge on the capacitor. It's just a number that we use to characterize how long it takes to charge or discharge this capacitor, how long it takes to have this growth or this decay occur. The time constant is equal to R times C. You might hear time constant elsewhere as you deal with these things, whether it's in biology or whether it's in some other thing that occurs over time that will decline or increase over time. You can see it in chemical reactions as well. I think, in fact, in PChem, you'll deal with capacitor circuits for a similar reason, because you're dealing with growth and decay functions. The units for the time constant are in seconds. And so if you think about this e to the minus t over RC, notice that this is a dimensionless number because I have seconds, and then I also have seconds here. So this denominator of the exponent is really just to give you a characteristic time. If I were to look at my graph up here, I don't know, the time constant is, where is it? It's something like right here. It's right about there. So this is about 1 tau, 1 time constant. Okay, y'all clear? The time constant is not the time to charge or discharge. In fact, the time to discharge or charge a capacitor is actually about 10 time constants. And at that time, we say that it's about 99% charged or discharged. So out here, this is about 10 tau. This is a characteristic time. It helps us to describe how long it takes to charge or discharge the capacitor, or whatever system you're dealing with that acts in this exponential way. And in order to fully charge or discharge, we have to get through about 10 tau. Now that's important. I'll probably ask you on the test when you have an RC circuit, I'll ask you, well gosh, how long did it take to fully charge or discharge this capacitor? And you would just calculate the time constant, and then you would multiply that times 10. I might also ask you, what is the time constant? What is this characteristic time? And then you would just calculate this R times C. Often, I'll give you values for R and C. Like say I'll give you a value for R that's 2 mega ohms, and I'll give you a value for C that's like 3 microfarads. I do that just to make it easier. Well, one, often our resistors are like this, they're mega ohms, and our capacitors are microfarads, and this gives us a time constant of tau equals R times C, which is 2 mega ohms times 3 microfarads. Notice the mega and the micro cancel out and just leave me with 6 seconds. So that gives me a capacitor that takes 6 seconds to charge and 6 seconds to discharge, or something like that. I do that just to make the math easy for you, but also sometimes it's nice to have a timer that has a time constant of about a second or so, on the order of a second. charge, discharge, charge, discharge, to give you this regular timing. You can use these circuits for things like flashing lights. You ever see your flashing lights, your turn signals on your car? They use capacitors. And the way it works is they charge the capacitor, and then it discharges through your light bulb. They charge the capacitor, and then it discharges through your light bulb. And it does it at this very regular rate, which is based on the time constant. Makes a very nice and easy way to create a timed circuit. All right, let's try this quick test. Here I'm looking for, in this RC circuit, what is the time to fully discharge the capacitor. All right, let's stop at 110. 110. 110, just a few more seconds. Let's see. This is right. So those of you that answered B, you gave me the time constant, but I really want to know what is the time to discharge this. In order to find that, I first have to find the time constant, R times C. That's 1 megohm, 4 microfarads, and that's equal to 4 seconds. But the time to completely discharge is going to be 10 times tau, which is equal to 40 seconds. So A is the right answer. If I'm looking at the plot of Q versus T, it's going to start up here, and it's going to decline like that. Our time of 4 seconds is going to be right about here. We get about 2/3 of the charge is going to decrease at about that time. And then out here, we get about 40 seconds. Also notice the total charge here. That is the charge, the maximum charge right here. This wasn't part of the problem, but if I wanted to know the total charge, then I would say Q is equal to C, which is 4 microfarads, times V, which is 2 volts. So I would be starting out with 8 microcoulombs of charge. And then it would take about 40 seconds for us to get rid of all of this charge. With an exponential growth or decay, you never actually get to 0, or you never actually get to the maximum value, but you approach it, right? That's the way these curves work. Y'all have had some experience with exponentials before? In physical systems? Nobody's saying? All right, no. Okay, well that's okay. Listen, there are a couple of homework problems that you should look at and make sure that you can work them through. Once you do them a couple of times, they're not that complicated, but just make sure that you can do so. And I also wanted to point out, this came up to me recently, that somebody didn't know, I forget who it was, but somebody didn't know that the solutions for the homework are online. I pointed this out at the beginning of the semester, but I just want to make sure that that's clear. That if you go to Physics 202 homework here on the page, this has all the homeworks from your workbook. Right, so if you want to print them out again, that's fine. But then it also has solutions to them. They're just sort of me talking through the homework problems. But you can also use those to find the particular problem that you're working and see the solution. I know many of you are aware of that, but let me just make sure that's clear. Okay, how about this one? What is the capacitance of this circuit? All right, let's stop at 35. 35. Okay, good. C is right. Those of you that put D, make sure you check the units. I don't usually change the units on the test because that's a little underhanded. But notice here that we have units for coulombs here, not farads, and our unit for capacitance is farads. So my time constant tau equals 1 second. My resistance is 10 megohms, and 1 second is equal to 10 megohms times our capacitance. And we find you can change this to SI units, 10 times 10 to the 6 ohms if you like. And then you find that C is equal to 1, or rather 0.1 times 10 to the minus 6 farads, which is 0.1 microfarads. 0.1 is 1 over 10. All right, we're going to move on to household circuits. We'll see capacitors again, and make sure that you look at the homework, okay? I'm not going to work them here, but look at the homework. It'll help you to sort of work with the mechanics of that equation. And if you need help with that, working with the mechanics, just the math of it, then please come see me. I can help you in 5 minutes, and you'll have it, okay? But let's move on to household circuits. You'll need to know several things about your house. You'll need to know how the house is laid out. It's laid out in parallel. You'll need to know sort of the basics of how electricity gets into your home. And then you'll need to know 3 safety features. You'll need to know about the GFCI, the circuit breaker, and then also as the grounding of your circuit, your home. So in short, beginning, 3 wires come into your house off of a utility pole. Actually, there's a transformer on your utility pole. We talked about transformers before, and in a later chapter we'll see how they work when we get into AC electricity, how you have this changing electric field, magnetic field, which inducts another current into that will actually come into your home. So we'll look at transformers later. But these wires include 2 hot wires. If you're looking in your home, that's usually the black wires or the hot wires. They include 2 wires. These are at plus 120 volts and minus 120 volts, and a neutral wire. Sometimes you'll hear this referred to not as 120, but as 110 volts. I'm going to use 120. It's sort of a difference in how you think of it. 120 is the maximum, and then 110 is a little bit different, but I'll just use 120 for now, and then we'll talk about that later when we get into AC electricity. All right, you might know that in your home, that on the outlets, like I brought them off up here, on your outlets, those operate at 120 volts. You might have seen that on your devices that you have, that this needs 120 volts, or sometimes it says 110 volts. But did you know that there are other devices in your house that operate at different voltages? Which are those? No, not light bulbs. Dryers, central units, like clothes dryers, heating units. What else?
Microwave.
Your stove, right? Your electric stove. No, your microwave operates. You're guessing, aren't you? That's okay, Brennan. I appreciate that. So you have some devices that operate at higher voltages. They actually operate at 240 volts, or sometimes they say 220. So you might have heard both of those. And that comes about from these 2 hot wires. Most of the time, you're only using this. This wire you'll use for the outlets here. These all operate at about 120 volts. But when you need 240 volts, you use both of these wires. That's why, like on your clothes dryer or your electric stove, that instead of having a 3-pronged outlet, you have how many prongs on those outlets? You have 4 prongs. 2 of those, one is plus 120, one is minus 120, one is neutral, which is that 3rd wire that comes in off your utility pole, and then the 4th one we'll talk about. It's actually a grounding for your house. So this allows us to have both devices that operate at 120 volts and 240 volts. Let's write that. 120 volt devices, and 240 volt devices. And these are the big power hungry things of your home. The electric heaters, like not like the little bathroom heaters, but the big central heaters, ovens, AC units, etc. Not the little window units, but the big AC units, the ones that need a lot of electricity. We talked about this recently, and we'll talk about it again, but why would you want to have a high voltage for your power-hungry devices? Why would you rather have 240 volts instead of 120 volts? What happens if you have high voltage for a given power? What happens to the current? If your voltage goes up, your current goes down. And so it's the same reason that we have 30,000 volts going across Texas to come to us. It doesn't come from Texas. I think it comes from New Orleans, our energy. But the same reason when you have these very high voltage transmission lines, they have those things going at very high voltages because it decreases your power losses, because it gives you a low current. So when we have a lower current, it cuts our power losses. Okay? Y'all know that? At your home? Some of you do? Okay. Well, you have these three wires. They come in from your home. Here's your plus 120, minus 120. There's your neutral that come in. Here's your utility pole. There's a big bucket on top of that, and that's your transformer. And then they come in. They go in through your meter that has those little numbers that move around. You ever look at the numbers, the dial that goes around, the little merry-go-round? Yeah, so they come in through a circuit breaker, which we'll talk about, and then they go out into your home. And they go into your home as a parallel circuit. And they do this for a couple of reasons. First is so that all devices will operate at the same voltage. And second is so if you remove one item or one device, if you turn it off, the others will stay on. And they're unaffected. What I mean by that is sort of the same as part one. Is that, remember, if we have 3 resistors in series and I take one out, then the voltages to these other 2 resistors will increase because they reallocate the voltage that they had spread across 3 resistors. So by having your house in parallel, the voltage to any single device will always be constant. It's sort of hard to think about why these are in parallel, but look, I brought a piece of wire. This came from our house. And so it has 3 wires inside of it. I'm going to pass around. But just forget about the bare wire for now. We'll talk about what that's for. But this is our hot wire, the black, and then the white wire is the neutral wire. The same ones that come in, they're connected to those wires that are coming in off the street. The plus 120 and the neutral wire, which has no voltage at all. And so if you think about how they come in through the house, I have this sort of mock-up of a wall. I have electricity that comes in through the meter. Can y'all see this over there, Cyrus? You can stand up if you want and come see. But I have electricity that comes in through the utility pole, and then it comes into a switch here, and then you can think about these wires that are spreading out into parallel circuits. So I have, a wire that's here that has 2 pieces to it. Let me draw that last outlet. It's a resistor. It has 2 wires, and then it goes to the other resistor right there, and 2 wires, and a resistor, and a resistor, and then a light, and then a switch. So I have these sort of a daisy chain type thing, but it's actually going to be laid out in a parallel circuit. So your entire house is laid out as multiple parallel circuits. Each individual circuit is parallel, and then you'll have multiples of those circuits. Several safety features in your household that you need to know about. You need to know what they do and how they do it. The circuit breaker. the grounding. That's that bare copper wire that you see in that Romex. That's sort of the brand of it. And the GFCI. Or sometimes this is called just the GFI. I'll tell you what that means. You need to know what each thing is and how it works and what it protects you from. You might, for this, you'll probably have like a short answer while I ask you, describe what the GFI does in 1 to 2 sentences. That sort of thing. So a circuit breaker or a fuse turns a circuit off if the current exceeds the safe capacity of the circuit. The total current exceeds the safe capacity of the circuit. See those wires that you run through your house? They're rated for a particular current. Like I think that's rated for 20 amps. And so if you put more than 20 amps through that wire, then it's in danger of heating up, melting, and then, you know, catching fire in your home. So you don't want more than what's rated for your system in your home. Some are 15 amps, some are 20 amps, some are 30 or even more. So most household circuits will turn off if the current exceeds 15 amps or 20 amps. But you can have 30 or 60 amps as well. This is a picture of a circuit breaker. Most of you probably have circuit breakers in your home. Some of you might have fuses. Or if you have an older house, you might have a combination of both. Like we have fuses and circuit breakers. The fuses will often look like this. They sort of look like a light bulb on the bottom, like that, and then they're sort of chopped off on the top. You screw them in like a light bulb. And then if you look at the top, there's usually a glass panel that has a metal tab across it. And when the current gets too big, what happens to that metal tab? The metal is going through the metal. The current is going through the metal tab, and when it gets too big, it does what? Yeah, it sort of explodes in there and burns out, and you just leave sooty, and then you see that it's done. Some of your fuses will look sort of like shotgun shells, and those are for your higher current fuses. Okay? But they serve the same purpose. They just turn off when the current gets too big. With your circuit breaker, if the current gets too big, you just go and you flip the switch, and it goes back again. But with the fuses, you have to actually, you know, drive to Lowe's, buy some more fuses in the middle of the night, and then plug them in, and it's kind of a hassle. Fuses can work in a couple different ways. This one, we don't really use it anymore very much, is use a bimetallic element. Let's see, we didn't do thermal last semester, did we? Well, when you put two metals together and you heat them up, one metal will expand at a faster rate than the other metal. And so if I have two metals and I heat them up, one of them is going to get bigger faster than the other one. And what that's going to do is cause it to bend in one direction or the other. You ever seen those old thermostats? They're round usually. You take the cover off and there's a coil of wire in them, coil of metal. No, you haven't seen that, have you? Okay. Those operate by the same idea, that when the temperature changes, that coil will get tighter or it will loosen up. All right, so some of our circuit breakers work like that. When it gets too hot, this metal bends and it turns the circuit off. Most of them now work by electromagnets. Don't worry about it too much right now because we'll talk about it. It's sort of like a solenoid switch, if you know what I'm talking about, where you have a coil of wire with a metal, like a metal rod inside of it. And when you put current through that wire, it creates a magnetic field. If you put too much current, it will engage that metal rod and move it into position. So this is more common to have this electromagnet type setup in your circuit breaker. But the end result is that if your current gets too big, it turns off. Okay, let's try this. Remember, your power is equal to your voltage times your current. You have a number of different devices on your circuit, and when an electrician is designing your electrical system, he or she takes into account the number of devices that you'll use on a particular circuit and the types of devices that you'll use. Like, will you use a bathroom heater? Gosh, that draws a lot of current. Or will you use a hairdryer? That draws a lot of current. And you can calculate, in a given situation, how much current will you have going through this circuit. That's what you need to do here. All right, let's do about 10 more seconds. We'll stop at 2:05. All right, doing very well. 2:05. I have a good joke for you if you do well. Are y'all gonna get it? Let's see. It's a good chemistry joke. That's close enough, right? All right, let me finish this. So here on a circuit breaker, our current is P over V. So this would be 1200 divided by 120, which would be 10 amps. So you get 10 amps from the heater, 1 amp from the light for a similar reason. 120 over 120 is 1. 1 amp here. So when it's running, I have 12 amps. But then I add 4 amps, 480 over 120. So somewhere between 12 and 16, I've maxed out my circuit. And so you pick the number that's between 12 and 16, which is 15 amps. Here's a joke you can tell your chemistry professors. You ready? What do they do when a chemist dies? They bury him. Are you going to tell your chemistry professors that? You tell Marlo? Okay. All right. Let's look at grounding. Know what circuit breakers are. Be able to calculate the current on a particular circuit. Okay, so grounding is if your house is newer and you look outside by your meter, if you look down, there's a little copper wire that comes down the side of your house and it connects to a rod that's driven deep into the ground, 8, 10 feet maybe into the ground. Y'all know what I'm talking about? Have you ever seen that outside your home? Yes? No? Okay, if you have an older house like us, then you might not have that. So our house is actually grounded to the plumbing, which you can do as well, where the electrical system is connected to the plumbing, which also goes into the ground. But most houses have this grounding rod, it's a brass rod, and you have a piece of copper wire that's connected there. This piece of copper wire goes directly to the outlet. You have this hole, sort of looks like the mouth on the face of this guy, the round hole, and then that goes directly to the bare copper wire that you saw when I passed around earlier. So this bare copper wire, which goes to your appliances, is connected directly to the brass rod outside your house. It provides a direct connection from here to the brass rod. So, serves a couple purposes, the grounding rod. It really serves one purpose, but that primary purpose is to protect you from faulty devices. And the second is sort of to protect your house from lightning strikes, or protect your electrical system from lightning strikes. That is, if you have your house and you have the wires that are running throughout it, they're all connected to the ground out here. And so if you get a lightning strike, it comes here and it charges the system, and that extra electricity will go out through the ground. I have just a light bulb here. A couple things I want to show you. Notice here, these are the outlet. One of these is a hot wire. That's the black wire that you saw in that yellow cable that I passed around. And what's the other one, the other eye? One of them is hot wire, that's at plus 120. What's the other one? That's your neutral wire. So if I put this into here, light bulb will come on. Right? Let's see, which one of these is hot? I think this one's hot. Let's do it over here. That's the GFI. There's an outlet back there somewhere, yeah? Where? Got one next to me. I'll do it over here. I can get up if you want to come see. This is kind of cool, actually. You want to come see? Hopefully I don't die. So again, I can put them in here, and I get one's neutral and one's hot. I think the short one is hot. Let's see. Yeah, so see the short one right here is hot. That's at plus 120. And notice, you don't want to do this right away because if somebody's working on the system, they can get shocked. But I can run electricity into the ground instead. So now the electrons are coming out of the hot wire, and then they go into the ground, which is outside the building somewhere. They go through the light bulb, but then they go into the ground, like that. But notice, what do you think will happen if I put a wire here and a wire here? What's going to happen? Nothing, because I'm hooking it up to the neutral wire and then to the ground wire. There's no electricity at all flowing through these parts of the circuit. There are when you connect them to the hot wire, but otherwise there's nothing. You can stick a paper clip in either one of these holes and you'll be just fine. So tell your 6-year-old cousin or whatever, hey, you can put a paper clip here, and then if the electrician has wired it up correctly, you can also put a paper clip in the long side too. Okay? So that's the ground, and it hooks up directly to the grounding rod outside your house. If you have a faulty appliance, you ever taken apart your computer? There's a green wire inside the computer, and it's connected to what? It's connected to the ground. It's actually connected to the case of your computer. So there's usually a green wire in your computer. There's a little screw that connects it to the case of the computer, or some other device that you might have. So if you've ever seen a green wire that's screwed to the case in some way, that's your ground. That takes that device and connects the case of the device to that third prong, which is connected to that brass rod outside your house. So it provides a direct path for any electricity to go through the case, out through the wire, and into the ground outside your house. So this third prong offers an alternate a direct path to the grounding rod outside your house. So if you imagine this electrical device, say it's a toaster or something, and it goes along and it's working just fine. But then something happens inside the toaster. A wire gets knocked loose, or a wire burns up, or something happens that causes it to malfunction. And that wire touches the case. Now when you get current coming into the device, it's going to not go through the device, but instead it's going to charge the case. And if you don't have the grounding, then that current will go, through you and through to the ground, and it'll hurt you. It might not kill you. It could kill you, but it'll hurt you. But alternatively, if the case is grounded, that electricity will come out. It'll come out here. It'll say, I don't want to go through that guy because it's too much resistance. Instead, I'm going to go out this way, and then I'll go outside your home and go into the ground through that grounding rod outside your house. So the third prong provides an alternate ground for your devices to protect you from these faulty devices. All right, let's try this. All right, let's stop at 30. I'm doing this 5K this weekend, the CAP 5K, Colonels Against Trafficking. Y'all heard of this? Yeah. And so I went out this morning for a run, and it was really foggy, right? And so I was going to try to catch some like this, but I missed. Oh, it provides an alternate ground. Make sure you can describe what it does in a couple of sentences. It'll probably be a short answer question. I'll ask you to describe one of these features. You'll see that in old test questions too. All right, let's do the ground fault circuit interrupt, and then we'll wrap up. The ground fault circuit interrupt, this is called the GFCI, or sometimes it's just called the GFI, ground fault interrupt. It's an outlet that looks like this. It has a little test reset buttons on it. Sometimes you see it on devices, not on the actual outlet, but you'll actually see it on the plug. You got that red and yellow button. What kind of devices do you see this on, or where do you see these types of plugs? Bathrooms, where? Okay, you see them in bathrooms. What type of devices do you see them on? Hair dryers. What? Straighteners. Oh, yes. Yeah, I was using my straightener this morning, and the GFI went off. Anyway, you use them in areas that are prone to be what? Wet. Right. So you use them outside in kitchens and bathrooms. So you use them in areas that are prone to be wet, bathrooms, kitchen, outside, on hair dryers, etc. And what this consists of is a very sensitive ammeter. And if ever IN exceeds I out, then it will turn off in a millisecond or less. So imagine I have a wire. This is my device. I have a wire carrying current in, right? That's the black wire. And then I have a wire carrying current out. That's the white wire, the neutral wire. Imagine what would happen if this current was bigger than this current. Because your GFI is constantly measuring those two currents. There's a little ammeter in here, and it's always, like every millisecond, it's saying, what's I in? What's I out? What's I in? What's I out? And it compares those two values. So what happens? What does it mean if the incoming current is bigger than the outgoing current? What does that mean? It means what? No, not necessarily. It means that you're losing current somewhere, right? That not all the current's coming out that's going in. That means that that current is going somewhere else. Where is it going? Or into the water, or into you, even worse, right? So what this does is it always compares those two currents, and it asks if they're ever different to within some, sensitivity, then it'll turn off the circuit. So it's a very sensitive ammeter. That's why sometimes it turns off just when you try to plug bare wires into the outlet. That you get a little spike in the current, and it'll just turn off. Okay? It's also sensitive, so that's why you need to test it occasionally to make sure that it's working. Did you know also that when you have a GFI here, I don't know if you noticed before, I was actually plugging the light bulb into this outlet, right? But did you know that if you have a GFI on a circuit, then it protects all of the outlets that are in that wall. So if you have one GFI, the electrician will put it first, and then it will protect all the outlets in your wall. Don't know that? So you should only have one GFI in your bathroom, but it protects all the outlets in your bathroom. But we just have one outlet. Our bathroom is like 10 square feet. Literally, it's like 3 by 3 feet. I'm serious. We had to special order a sink to put in our bathroom. It's like this big. And my wife and I, we just sort of stand there going brushing our teeth, and it's like, okay. But we like it. Like we wouldn't have any other bathroom because it fits us. All right, so what does a GFCI do? All right, let's stop at 20, and then there's one more, and then we'll call it a day. Okay, a GFCI turns off if IN is bigger than I out. Make sure that you understand the difference between this and this, because D isn't for a GFI. What is D for? What is D described? A circuit breaker, right. So those look very similar, the GFI and the circuit breaker, but they're actually different. So make sure that you understand that. C, by the way, here is the grounding. And now we have one more, I think. So again, on the test, I could ask you to describe a particular device. I might ask you just to describe any device that you want, any of the three devices. Or I might ask you to just write, a few facts about the household circuits. Things like things like we see here. But it'll be a free response, a few sentences that you'll need to write. Probably 5 to 7 points. All right, let's stop at 40. Okay, let's see. The household is a parallel circuit. Is that right? That is right. Do they operate at the same current? No, they operate at the same what? Voltage, right? So you can make this correct by making current voltage. As you add more devices, the potential across each device decreases? No, the potential is actually constant. Because they're in parallel, the potential will always be the same. And this circuit breaker, this isn't describing a circuit breaker, it's describing the GFI or the GFCI, the ground fault circuit interrupt. So A is the right answer here. All right, y'all have a great day. I'll see you Friday. I think we might have a few more concept test questions on this chapter, which we'll do, but we'll move on to the next chapter on Friday.